Okay, so today we're finally going to start doing some real mathematics. Introduction to Fourier series. Introduction to Fourier series. Okay. There's some basic knowledge that I think you all are familiar with. One, the function classes of functions. First are the continuous functions. I always abbreviate continuous as CTS, and functions as FN. Continuous functions. Two, the piecewise continuous functions. You all know what piecewise continuous means, right? It means that has a finite number of discontinuities. And for now we are on a finite interval, so finite number of discontinuities. Okay. Number three, we've got the Riemann integrable functions. Which we talked about earlier, right? They are functions for which you can take, given any epsilon, you can find a partition for which the upper and lower sums based on those partitions are within epsilon of each other, right? And four, we have these things. This is not a real class, but we have functions on the circle. It's basically functions. So functions on, say, the unit circle, and we identify those with with periodic functions. So let's do it like this. Let's say on the circle. So you can have a function of the angles. Right? A function of the angles. The angles range from 0 to 2 pi, say, or from negative pi to pi, or whatever you want. Right? And the thing is that f at 0 has to be f at 2 pi, right? And so we identify those with 2 pi periodic functions on the line, on the real line, right? 2 pi periodic functions. So those are classes that you should be familiar with. And now we give our main definition, that of the Fourier series. Okay. So you have I should say that in this text we're going to assume that everything is Riemann integral. Okay. Everything is Riemann integral. That's actually not the usual setting for Fourier analysis. Usually, if we don't do it this way, then I cannot teach this course. I have to wait until you all take 138. Then I can teach the Fourier analysis. So we're going to assume that everything's Riemann integral, because otherwise I'll never be able to teach this course. Given an integrable function, so you have some integrable function on an integral, so Riemann integrable, which we'll just always call integrable. We define the Fourier series. The Fourier series of f is defined as summation f hat and e to the 2 pi I n x over L as n ranges from negative infinity to positive infinity. Okay, so it's a function of x. It's a function of x, and we take the sum of these exponential functions weighted by some coefficients. Okay, so you've got a bunch of exponential functions, with different frequencies. Right? different frequencies. The ends range from minus infinity to positive infinity. And you've got these coefficients that you put on them, and then you sum all these guys together. Okay, where the coefficient f hat n is defined as 1 over L integral from a to b of f of x against e to the minus 2 pi I fx over L dx. I'm sorry, L where L is b minus a, the length of the edges. Okay, and so this thing is called the Fourier series, and one writes f twiddle the Fourier series to say that this thing is the Fourier series of f. We're not saying that it's equal because it may not be equal. Okay, and then these guys are called the Fourier coefficients. The Fourier coefficients. Okay, and remember last time the analogy between Fourier analysis and linear algebra. If we define an inner product, right? So one defines an inner product. F against G is 1 over L, the integral from A to B of F against G bar. F against G bar, right? And what you see in the Fourier coefficient is really that you're taking the inner product of F against e to the 2 pi I and x over L. Right? And you're taking the inner product against this guy, and then you're taking that weight, right? You're taking that coefficient and weighting exactly that function that you took the inner product against with that weight, and you're taking the sum. So this is just like you've got an orthonormal basis, right? You've got an orthonormal basis, I, you take some vector, right? Some vector, and you know that the vector is some combination of the orthonormal basis. Well, what are these coefficients? You know what they are, right? The coefficients are the inner product of B against DI, right? And so this is exactly what we're doing here. Okay. So this is except it's infinite. There's an infinite number of basis functions. Okay. So far so good. Okay. So let's do an example. Example maybe beneath you, I don't know, we'll see. You have some function, f theta, that's defined as theta times pi minus theta. So this is one of the homework exercises. So defined on 0 pi, it's defined there, and we make f a 2 pi periodic odd function. So right now it's defined only on 0 pi, then we make it odd, so it's defined on negative pi, and then we extend it in a 2 pi periodic manner to the whole line. And let's calculate the Fourier series. So notice that on negative pi 0, the derivative is pi plus 2 theta, and on 0 pi, the derivative observe. Okay. And then we're going to calculate the Fourier series. Well, we just need to calculate the coefficients. Right? So we take the integral from negative pi to pi of function against the complex conjugate of e to the I of theta. Right. And what you do is you use integration by parts. So integration by parts, you get 1 over 2 pi times negative f theta over I n d to pi and theta between negative pi and pi, plus 1 over I n integral negative pi to pi prime d to the negative pi and theta d theta. Okay, and then by periodicity, because this thing that we're evaluating here is 2 pi periodic, this becomes 0. This part becomes 0, right? And then we're left with this thing. We're integrating, right? So we're using integration by parts, right? We passed the derivative from this guy over to this guy. Happens when you integrate by parts. Right? And now you see why I wrote up the derivatives. Right? We'll break this thing into 2 pieces, depending from negative pi to 0, from 0 to 2 pi. Right? And you end up with 1 over 2 pi 2 n integral from negative pi to 0 of theta e to the negative pi n theta d theta minus the integral from 0 to pi of theta e to the minus pi n theta d theta. I don't know if you want to copy this down. I will send out the notes later. Right? So, and it's just integration by parts. Okay, so. You do some thinking. There's a couple of tricks involved. Maybe I'll leave it to you. Maybe I'll give this as a sort of one of the homework problems. You end up with how far should let's say this. You end up with this sort of thing. Which turns out to be negative 1 to the n plus 1 plus 1 times 2 over n cubed pi I, which is, it's going to be 0 if it's n is even, and if n is odd, then you get 4. So you get 4 over n cubed pi I if n is odd. And 0 is. So sort of like a super calculus 2 exercise gives you the Fourier series, right? So the Fourier series that so this function that is basically the Fourier series of this function that is the sum over all odd n, negative and positive. We get 4 over n cubed pi e to the You just calculate them. You just calculate them. So like
from negative pi to 0.
From negative pi to 0. So like the function. So you have this function and you extend it in an odd manner first to the negative. So right now, first in the problem it's given to you only on 0 pi. Okay. And there you see that the derivative is the derivative is just pi minus 2. I think unless I made a mistake, you extend it in an odd manner and then calculate the derivative in, and you get that. Right. Over here, I think f theta is going to be theta times pi plus theta on the left hand side. And so you get pi plus 2. So nothing. You should be embarrassed. No, you shouldn't. Okay, so as you see, this is a Fourier series. Okay. I'm glad I can tease you guys because the calculus students are not easy to tease. Very sensitive. Okay. So this is an example of calculating a Fourier series. We do not know if this means anything, right? We don't know if this gives you back your function, or in what sense it gives you back your function. Does it converge pointwise to your function? Does it converge uniformly to your function? Does it converge to your function? Right? We don't know any of these things. And in fact, we know that talking about pointwise convergence is futile, right? From the beginning, because if you look at the definition of the Fourier coefficients, you notice that if you change your function pointwise at, say, a finite number of points, then the integral doesn't change, right? If we take one function and we take another function, which is exactly the same, but just changes at a finite number of points, these integrals don't change, right? Because this finite number of points don't matter, right? And so the second function has exactly the same Fourier coefficients. We'll have the same Fourier series, right? So asking to recover the function pointwise is meaningless. We know from the beginning it's hopeless. Right? In fact, it's worse than that. It's not just a finite number of points. If you change this on a set of measure 0, then if you change it on a set of measure 0, which can be a countable set, right? It still doesn't change. Well. No, now I stepped into past 138. Forget what I just said. Forget what I just said. Because, forget what I just said. Anyway, if you change it on a finite number of points, same Fourier series. And so you cannot hope for that. And another thing is that we really haven't even explained what we mean by convergence of the Fourier series, right? Because here we're talking about from n equals minus infinity to infinity, f at n e to the I n x, right? N goes from minus infinity to infinity. What do we mean by that? Do we mean that we break it into, because you're perfectly comfortable with saying from 0 to infinity, right? That makes sense. But what do we mean by come from minus infinity to infinity? You could break it up in a couple ways, right? You could say we're going to break it up from 0 to infinity and from -1 to negative infinity, right? That would be a reasonable way. That's not what we're going to do. In this book, we'll always mean the following, that the limit, what we mean by convergence, so let me just be more formal about it. We define the nth partial sum. The nth partial sum of the Fourier series F by S and Fx as the sum of the Fourier series Fourier series as n ranges from minus n to n. Okay, so we're going to do it in a symmetric manner, right? We're going to go to negative and positive infinity evenly, okay, rather than doing it in two pieces. It's not the same thing as asking if it converges in those two pieces. Okay, and so whenever we talk about convergence of the Fourier series, we mean does this limit converge to the function? Convergence of the Fourier series to f is going to mean there's a limit of the Sn f. Does the limit of the Sn f equal f in some sense? Pointwise or uniform. I'm glad you all made it.
It was really hard to find a printer in the state word.
Okay, don't worry. Well, I'm glad you did. I was worried that you guys had dropped. Okay. So, and that was the most important thing you learned all semester. Just teasing, the name of people. Yeah, a friend of mine, when I was an undergraduate, really smart guy, and he ended up like skipping classes because he didn't really need to attend classes. One day we were taking this, he was taking a course in algebraic topology. And he walked into the class. And so the professor said, okay, so as we proved last time, he started picking up all this advanced stuff. Like that nobody, like maybe stuff from a graduate course, just to scare like that.
He's something
He's like, so you got this, the cohomology sequence of something. Anyway, so. Okay, so what we've just done is just define the Fourier series, right? Define the Fourier series, and then we did an example calculating the Fourier series. That's just calculus. It could be tricky calculus, but it's just calculus. And then the important thing here is that we define what we meant by convergence of the Fourier series. And what we mean is that these partial sums we're going to take our convergence, we're going to take the limit as the upper and lower guys go to infinity at the same time. As I just said, when you're talking about something like from negative infinity to infinity, it could be that you're talking about breaking it into two sums from -1 to -infinity, say. So you could break it into two sums. That would be a reasonable way. But we're going to take this symmetric partial sum tending towards infinity and positive infinity, some negative infinity and positive infinity simultaneously.
But I don't know if this is true or not, but if you initially take just the partial sum, isn't it true that like a subsequence that converges doesn't necessarily mean that this whole sequence itself is convergent? Or am I interpreting it incorrectly?
So this is the partial sum sequence, right? This is the partial sum sequence, right? We've got this thing, negative infinity, positive infinity. I mean, this doesn't even make any sense. Right? It's true that if you have a sequence of points and some subsequence converges, then that says nothing about the entire sequence, right? But that's not that's not really what we're talking about here.
Oh, because, it's limit is big N approaches infinity.
Yes, yes, we define a new sequence. Just remember how you were talking about, sum. How did you define the sum of an infinite series? Right? How did you define an infinite series? Right? Well, k equals 1 infinity. What did this mean? What did it mean for this to converge? Well, you created a new sequence. You created a sequence, right, where k ranged from 1 to n, right? You created this new sequence, the sequence of partial sums,
Right.
and convergence of the series was defined to be that the sequence of partial sums converged. Okay, so convergence of a series was defined in terms of your previously given notion of convergence of a sequence, right? And it's the same thing, right? So what does it mean for our Fourier series to converge to the function? It will mean that the sequence of partial sums, what kind of partial sums? Symmetric partial sums, converges to the function in some sense.
Yeah, I don't think we ever used that definition of convergence in the very one.
This definition of convergence?
Yeah, I don't think we did.
Yes, you did. You must. If you didn't do it in 131, you did it in calculus 2.
Okay.
You should have done it. You should have done this in calculus 2.
Okay.
And if you didn't, you should go back and send an angry letter to your teacher. Yeah. I once taught students who sometimes they came from places where the preparation was extremely poor. And one student was so incensed by his poor preparation that he said, "I'm just going to write an angry letter back to my high school." And really, some of them came from very bad high schools. Yeah, because they don't know that their preparation is bad until they compare themselves with others. Okay. So at this point, let's introduce a couple of constructions from some important constructs. It's a little bit of a digression to introduce these, but not too far of a digression. So first, there's this thing called the Dirichlet kernel. So the Dirichlet kernel, d sub n, is defined to be equal to the sum from n equals minus n and of e to the I x. Okay. So although I call it the Dirichlet kernel, as you see, n, it's really a collection of functions, right? It's a collection of functions as capital N ranges over the natural numbers. Right? So there's a whole family of these functions, and that's referred to as the Dirichlet kernel. So x is some variable that goes from negative pi to pi. And this is a fact or an exercise. There's a closed form expression for the Dirichlet kernel. Namely, it turns out to be n plus a half, sine of n plus a half times x over sine of x over 2. Okay. And the proof is in your book, right? The proof is to simply consider this is just a finite sum, so we break it into two parts. You break it into two parts, and then you recognize that each part is a geometric sum. Right? Each part is a geometric sum, and so you can use the geometric sum formula on it. Right? And then you get two things, you add them together, and it turns out to be this. But that's the trick. You recognize this thing as a sum of two geometric sums. You break it into two geometric sums. Fourier coefficients? What are the Fourier coefficients of the Dirichlet kernel? Jennifer? 1 and 0. And they're going to be 1 between negative n and n, and they're going to be 0 otherwise. Right? I mean, you see it, right? You just, if you want to, you can integrate this thing, against the appropriate value. You see that you get zeros, if I m x, if m is equal to n, right? Et cetera, et cetera. So that's pretty straightforward. So not a complicated question. The second construct is the Poisson kernel. Definition: Poisson kernel, and this is defined like this: PR theta equals sum from n equals negative infinity to positive infinity. R to the absolute value of n, e to the I n theta. Okay, so theta ranges from negative pi to pi, and r from 0 to 1. Okay, so again we have as r ranges from 0 to 1, we've got this family of functions. Right? Family of functions on the unit circle. And if you read the material on the heat equation, this actually turned up in there. Okay. Okay. And let me make an observation. Observe that this sum is absolutely convergent. This sum is absolutely convergent, right? Because what? Why is it absolutely convergent? Well, let's look at it. If we take this sum and from minus infinity to positive infinity, r to the absolute value of n, and let's take the absolute values. So we get absolute value of e to the I and theta. Right? Well, what's the absolute value of e to the I and theta? What? So we don't have to worry about that. Right? So we get this sort of sum, right? Right? And I guess in this case we're probably also doing like a symmetric sum, right? So we can think of this as basically summation, or twice the summation from say 1 to infinity r to the n, right? Right? Which is finite, right? Because r is smaller than 1. Right? It's a geometric series. R is smaller than 1, so this is finite. This is finite. Right? So it's absolutely convergent. Right? And if you think about it, that absolute convergence actually forces this sum of functions to be uniformly convergent. And uniformly also. It's also uniformly convergent, if you think about it. Okay, so now I'm going to ask the same question. What are the Fourier coefficients? What are the Fourier coefficients in this case? Of PR. What's PR at n? Jennifer? R to the n, R to the absolute value of n, right? And the reason this is sort of not a dumb question is because we don't have a finite sum anymore. Okay? So how did you get the Fourier coefficient? How did you get the Fourier coefficient? Remember how you get it? You take this thing, and you take the inner product, you take the integral of this against the complex conjugate of e to the I m theta. Right? Right? So let's recall how we get this, right? We get the integral of this thing, e to the I m theta, against the complex conjugate of e to the I m theta to get the mth Fourier coefficient, right? And so secretly we pulled out the infinite sum, right? We said that this is equal to the sum of la, right, r to the n, e to the I n theta, e to the I m theta, d theta, right? And then we use the orthogonality of these guys, right? Okay. But why could we pull out the infinite sum? Because we uniform convergence, right? And so it's not a matter of like a finite case where you just say, oh yeah, you can just look at it, right? Right? In this case, it's false. We don't know it's true that these things are the Fourier coefficients, except by the fact that this is uniformly convergent, and then we can treat it. It behaves like a finite sum. You can pull it to the integral. So be careful. Okay. There's another fact. The closed form of the Poisson kernel, 1 minus r squared over 1 minus 2r cosine theta plus r squared. And again, it's sort of done along the same way. It's sort of done along the same way. So I'll leave that to you to read. Okay, so now we're going to get to the first real theorem, of course, which is about uniqueness. Let me put up a statement. If the Fourier coefficients are all equal to 0, then the function must be 0. Equals 0 everywhere. What do you think about that? You already know that this statement is not true, right? Because we said earlier that you can't say anything pointwise, right? So this could not be true. This is sort of what we would like to be true, right? So this is a desirable statement. Desirable but false. This is what you would like. You know, if in the ideal world, right? If your Fourier coefficients corresponded uniquely, if your Fourier coefficients corresponded uniquely to functions, this is what would happen, right? Because the zero functions, Fourier coefficients should be this, right? And so if this happens, this should give you the zero function. Okay, this is what you would like to happen. Even though it's false, you have to ask, you know, in what sense is it true, right? To what extent is it true? It is true to a certain extent, and finding that precise boundary of where it's true is the game. Right? Okay. So here's the theorem, our first real theorem about uniqueness. If f is an integrable function on the circle. Okay, so let's say it's on negative pi pi. And suppose that all of the Fourier coefficients are 0. Let's say that all the Fourier coefficients are 0. If f is continuous at 0, then, I'm sorry, if f is continuous at some point, then the function is 0 at that point. So it may not be 0 everywhere, but wherever it's continuous, it's a 0 function. So this is pretty good. Okay. Okay. So I'm gonna erase what I just wrote. Is that all right? Okay, so here's the proof. And this is proof by contradiction. Okay, so without loss of generality, let's assume that that the point of continuity is at 0. That doesn't really matter. We can put it wherever we feel like. Let's suppose it at 0, just for simplicity. You'll see that the argument still holds wherever we put it. Let's assume that this guy is at 0, and let's assume that the value there is positive. That doesn't lose anything. Okay. So we know that our function is positive at 0, and then by probability we know that that in some continuity there exists some neighborhood, there exists some delta, such that in the delta neighborhood of 0, right, in minus delta delta, the delta neighborhood, right, the delta neighborhood of 0. In the neighborhood of 0, f exceeds 1/2 of its value there. Right? So we know it's continuous here, so there's some neighborhood where it just hasn't dropped too much yet, like that continuity. Right? So we're greater than half the value of 0. Okay. So and this is so what are we going to do? We're going to show that that the Fourier series so I'm sorry, we're going to go for a contradiction, okay, using, supposing that the function is non-zero at some point. Okay. So here's the idea. Let's create a sequence of trigonometric polynomials. As follows. Okay. So by trigonometric polynomial, I mean like finite linear combinations of the e to the I and x. So we create a sequence of trigonometric polynomials as follows. So our guys will be called piece of k. We let p just be the cosine function. We take the cosine function, right? We take the cosine function and we shift it upwards by some epsilon. So 1, this is 1. We shift it up by some epsilon so that where epsilon is greater than 0 but so small that outside of minus delta delta is less than 1 minus epsilon over 2. Okay, so outside of the, let's say that this is our delta neighborhood. Okay. This is our delta neighborhood. We choose the epsilon so small that outside of the delta neighborhood, we've moved up, but we have not, but we're still, we moved up epsilon, but we're still lower than 1 minus epsilon over 2. Okay, so we choose that epsilon to be really tiny. 1 minus epsilon over 2 is very close to 1. Okay, and so outside of the delta neighborhood, even though we've moved this graph up a little bit, it's still beneath that line. Second thing we do, so that's our choice of epsilon. Notice, since cosine is continuous, we can choose, we can find an eta, tiny eta, so that inside minus eta, the function, which is positive, exceeds 1 plus epsilon, is 1 plus epsilon over 2. Right? Because the function is 1 here, we've shifted it up by by epsilon, and we can choose a tiny eta here, so that inside there, we're bigger than 1 plus epsilon over 2. So we let p sub k theta be our p raised to the k power. And these guys are all trigonometric polynomials. They're finite sums of exponential functions. So here's the point. And we know that the Fourier coefficients are all 0, right, for all n. Right? The Fourier coefficients tell you being 0 means that f is perpendicular to the exponential functions for all n. Okay. So f is going to be perpendicular to any trigonometric polynomial. F should be perpendicular to any trigonometric polynomial. Okay. But what we've done is created a trigonometric polynomial, a sequence of trigonometric polynomials, where what happens? As you take these powers, well, the mass starts, the function starts heading towards infinity in the eta neighborhood. And outside here, outside the delta neighborhood, it shrinks down to 0, right? And so what we're going to get is that we shall see that f against the pk actually goes to infinity. Okay, because if our function were non-zero at some point, then it will turn out that the pk will pick that up. And the pk being concentrated more and more at 0 will pick that up, and will go towards infinity, even though it should be 0, and that will be our contradiction. Okay. So next time we'll start off with